What specific problem does eidetic learning aim to address in the context of artificial neural networks, and why is catastrophic forgetting a significant challenge for these models?
Eidetic learning aims to address the problem of catastrophic forgetting in artificial neural networks, ANNs, which is the tendency of these models to lose the ability to perform previously learned tasks when trained on new ones. This issue arises because many deep neural networks are overparameterized, allowing them to minimize training loss even with random labeling, but this excess capacity can lead to the loss of previously acquired knowledge. Catastrophic forgetting is significant because it undermines the effectiveness of ANNs in continual learning scenarios, where models are expected to learn and retain multiple tasks over time. Eidetic learning introduces a method, Eidetic Net, that utilizes the excess capacity of ANNs to ensure that important neurons for previously learned tasks remain unchanged during the training of new tasks, thus preventing forgetting. This approach not only preserves learned representations, but also enhances the efficiency and robustness of the learning process across multiple tasks.
How does the proposed method of eidetic learning work? Please illustrate the steps involved in training an eidetic net, particularly focusing on the process of iterative pruning and the conditions of persistence and resistance.
Eidetic learning operates by leveraging the excess capacity of artificial neural networks, ANNs, to prevent catastrophic forgetting through a structured process of iterative pruning. The training of an eidetic net begins with identifying the smallest set of neurons necessary to perform a given task, T_I, without loss of accuracy, denoted as N_T_I. The first step is to update a frozen set of important neurons, F, by adding N_T_I to it, ensuring that these neurons remain unchanged during the training of subsequent tasks. The second step involves reinitializing the neurons that are not part of F, denoted as R, and pruning the synaptic connections from these recycled neurons to the important neurons in F to satisfy the resistance condition. This ensures that the important neurons for previous tasks are preserved, persistence, and that the unimportant neurons do not affect the important ones in future tasks, resistance, thus guaranteeing that the network does not forget previously learned tasks.
Can you provide a detailed example of how eidetic learning operates during the training of two tasks, illustrating how neurons are pruned, frozen, and recycled?
Eidetic learning operates through a structured process during the training of two tasks, ensuring that the network retains knowledge from previously learned tasks. For example, when training on task T_1, the method first identifies the smallest set of neurons, N_T_1, necessary to perform this task without loss of accuracy. These important neurons are then frozen, meaning their weights will not change during the training of subsequent tasks. Next, the neurons that are not important for T_1 are pruned, and this set of pruned neurons is designated as R for recycling. When training the next task, T_2, the pruned neurons in R are reinitialized, and their synaptic connections to the frozen neurons from T_1 are pruned to ensure that the training of T_2 does not interfere with the performance of T_1. This systematic approach guarantees that the network can learn new tasks while preserving the knowledge from previous ones, effectively preventing catastrophic forgetting.
What are the primary advantages of using eidetic learning over traditional methods in mitigating catastrophic forgetting, particularly in terms of efficiency, accuracy, and model architecture requirements?
Eidetic learning offers several primary advantages over traditional methods for mitigating catastrophic forgetting. Firstly, it enhances efficiency by ensuring that the time and memory complexity of training is linear in the number of parameters, eliminating the need for rehearsal or replay, which is often required in other approaches. Secondly, it maintains high accuracy across tasks, as eidetic nets can be trained on significantly different subsequent tasks without harming performance on previously learned tasks, thanks to the structured pruning and freezing of important neurons. Additionally, eidetic learning does not require modifications to the model architecture, as it supports contemporary ANN architectures without necessitating separate batch normalization layers for each task. This simplicity in implementation, combined with a minimal number of hyperparameters, makes eidetic nets easy to train and deploy in real-world applications.
How was the effectiveness of eidetic learning validated in the experiments conducted? What specific datasets, benchmarks, and metrics were used to demonstrate its performance compared to other methods?
The effectiveness of eidetic learning was validated through experiments on several datasets, including the permuted MNIST, PMNIST, and CIFAR 100, using a deep residual network, ResNet 50. For PMNIST, a two-hidden layer feed-forward network was employed, and hyperparameters such as dropout probabilities and pruning strategies were optimized to ensure robust performance. The results indicated that accuracy on previously trained tasks remained constant even as new tasks were introduced, demonstrating the method's resilience to catastrophic forgetting. Additionally, the performance of eidetic nets was compared against other methods, showing competitive results in terms of task accuracy, as detailed in the provided tables and figures. Metrics used to evaluate performance included task accuracy and the ability to maintain performance across multiple tasks without rehearsal or replay, highlighting the advantages of eidetic learning over traditional approaches.
What limitations or challenges does the eidetic learning framework encounter, particularly concerning its application to more complex neural architectures or varying task distributions?
The eidetic learning framework, while effective in preventing catastrophic forgetting, faces challenges when applied to more complex neural architectures, particularly transformers. The paper suggests that making self-attention layers of transformers immune to catastrophic forgetting is challenging, if not impossible, due to the intricate interactions within these architectures. Additionally, while eidetic nets allow for efficient learning across tasks, the performance gap in task routing mechanisms indicates that as task complexity increases, the accuracy of task classification may decline, necessitating further research to enhance routing strategies. Furthermore, the framework's reliance on structured pruning may not uniformly apply across all layers, particularly in deep networks like ResNet 50, where the effectiveness of pruning methods such as Taylor pruning can vary. Lastly, the paper notes that while the method is designed to handle significantly different subsequent tasks, the stability of neuron importance across tasks may still be a concern, especially in scenarios with highly variable task distributions.